In this video, we'll practice calculating indefinite integrals. The integral of x to the n with respect to x is equal to x to the n plus 1 over n plus 1 plus a constant. So what we're doing is increasing the exponent on the x and dividing by that new exponent, and super important here to remember the plus c at the end of the expression. Formally, the integral represents the set of all possible antiderivatives of the function x to the n, and that's why it's important to have the constant on there so that we really are getting all possibilities. This formula is valid for any real number n as long as n is not equal to -1. Let's do a couple quick examples. If we wanted to integrate x to the 6th with respect to x, we'd increase the power by 1 and divide by that new exponent, and we need to remember plus c so that we're getting all possible antiderivatives here. So as a mental check, we're checking that taking the derivative of this expression here really does return the original function x to the 6th. So yes, that works. If we wanted the integral of, say, x to the half with respect to x, we'd increase the exponent up to x to the 3/2, and this time instead of dividing by a fractional exponent, we're going to think of it as multiplying by the reciprocal of that exponent. And again, the plus c is important here so that we're getting all possible antiderivatives. Let's evaluate the following integral with respect to x. First thing I'd like to do is rewrite that root x as x to the 1/2. Next thing we could do before integrating, let's multiply through. So we're going to be multiplying the x to the 1/2 times this expression here. And remember that the exponents are going to add as we multiply. So we'll have 2x to the 7/2 minus x to the 11/2. And we're still integrating with respect to x, so good idea to have brackets on there so that dx is multiplying both of those expressions. So now we're ready to integrate. Finding our antiderivatives, we're going to have 2 times x to the 9/2 times 2/9 minus x to the 13/2 times 2 over 13. And really important to have the plus c at the end of the expression here so that we're creating all possible antiderivatives. Finally, we just need to simplify. 4/9 x to the 9/2 minus 2/13 x to the 13/2 plus c is our final answer. Before our next example, it would be a good idea to do a quick recap about differentials. Let's say we have a function u which is equal to 12x squared plus 7. We could write the derivative of u with respect to x as du by dx, and that would be 24x. But we could also rearrange this expression to write du is equal to 24x dx. And when we write it in this form, we're thinking of du and dx as individual expressions. These guys here are called differentials. So let's see how we can use this idea in our next example. Let's evaluate the integral of 3x squared divided by root 5x cubed plus 2 with respect to x. This function here is too difficult to integrate directly, so what we're going to do is make a little substitution. Let's let u represent 5x cubed plus 2. The benefit of doing this is that now that denominator can be written more simply as root u. Now, if you decide to introduce u into an integral, then you need to figure out what du represents. So our differential du is going to look like the derivative, 15x squared times dx. Now looking back up at our integral, what we're really trying to rewrite is the remaining part of the expression. So we're trying to figure out how to write 3x squared dx in terms of u. So typically I'll just write something like this. 3x squared dx is equal to something or other, and let's look up at the previous line and figure out what it's equal to. Well, if we divide both sides of this expression here by 5, then we're getting 3x squared dx is equal to du over 5. So that's going to be the secret to rewriting our integral. We'll go up here and we'll say the product of these two things is equal to du over 5. So now we can say the original integral in the question is equal to the integral of du over 5 root u. Let's write that a little bit more nicely as the integral of 1/5 u to the minus 1/2 du, and then we can do our usual integration. So we'll leave the 1/5 out in front. The exponent on the u is going to increase by 1, so it's going to become u to the 1/2, and we'll multiply by the reciprocal of that new exponent, so 2u to the 1/2. And then really important here to add plus c, because the integral is generating all possible antiderivatives for that function. So now we've got 2/5 root u plus c, and to get our final answer we just need to replace u with the original expression involving x. So our final answer is 2/5 square root 5x cubed plus 2, and remember the plus c. So that is our final answer there. We've managed to evaluate that original integral by making a substitution.